Hello everyone, welcome back. My name is Mr. Cobalt, and in this video we're going to look at some molecules and ions, and we're going to draw some bonds, and we're going to label some hybridization bonds, some hybrid bonds, sigma bonds, pi bonds, all of that. We're going to draw some pictures, or I'm going to draw some pictures as best as I can, and hopefully I'll be able to explain this in a clear manner. So let's get into this. So here's the problem. So we're told to represent the bonding in each molecule or ion by drawing the orbitals, hybridized and unhybridized, of each atom in the bond. Label the sigma and pi bonds and label each bond by the orbitals that it is made from. For instance, the CH bond in CH4 would be made from the overlap of a carbon that is sp3 hybridized and a hydrogen with the 1s unhybridized orbital. You may draw the hybridized sigma orbitals as sticks and the unhybridized p orbitals as lobes for clarity and ease. Okay, so let's get into this. So we want to draw out the Lewis dot structures. We want to draw out the structure of each of these four molecules and ions such that we're going to show the bonding, the sigma bonds, the pi bonds, the unhybridized p orbitals, the hybridized orbitals, and all that. So the first thing I want to do is start by drawing the Lewis dot structures, since I think that is a good place to start, and it's going to show us what we kind of need to know, or what we need to show in our drawing. So HONO, or HONO, that's nitrous acid. So we'll draw the Lewis dot structure of that. I'll go over the Lewis dot structure steps quickly, but for those of you who may need a refresher for drawing Lewis dot structures, see my video on drawing Lewis dot structures, the steps and the examples and all that. It's there. So see my video for that if you need to. So for HONO, draw the skeletal structure first. You want to get the total number of valence electrons. So 6 for each oxygen, that's 12 total, plus 5, that's going to be 17, plus the 1, that's going to be 18 total. So we're going to draw our Lewis dot structure. So skeletal structure first, HONO. So there's the bonding. So next we used 6 electrons in the bonding. We're going to subtract that from 18. We get 12. We're going to add lone pairs to the outer atoms first. So that would be the oxygens. So we have 2, 4, 6. Ooh, let me draw that better. 6. That would be 8, 10. So 10. Okay, so then I have 2 left, and those 2 are going to go right there. Now I need to make sure everyone has an octet. So everyone's happy except for this oxygen, except for the nitrogen. So to give that one another bond, I'll move a lone pair from the oxygen, form a double bond. So there's my Lewis dot structure for HONO. Next would be this molecule here. So I'm going to have carbon. I have the 3 hydrogens bonded to the carbon. 1, 2, 3. So hydrogen, hydrogen, hydrogen. And then it's bonded to that carbon. And then that carbon is bonded to that carbon. And then we have this hydrogen here. Okay. So we need to get the total number of valence electrons. So I have 1, 2, 3 carbons, 4 valence electrons per carbon. That's 12, plus 1 from each hydrogen. I have 4 hydrogens, so that's 16 total. So I have 1, 2, 3, 4, 5, 6 bonds. That's 2 electrons per bond. That's 12. So I have 2 electrons left over. So I'll put 2 on this carbon, 2 on this carbon. Usually, the best way to go is to split them up and get some symmetry. So symmetry is best. So instead of putting both of them on one carbon, which you could do, it would work out the same way. you can the best way is to put the two pairs of electrons on both carbons, split them up, get some symmetry, and then go from there. In this case, this carbon needs 2 more bonds. This carbon needs 2 more bonds. So the only way we could do that is to create 2 extra bonds by using the lone pairs. So we're going to move the lone pairs and create a triple bond. So we'll get rid of those. So as I said, it didn't really matter since they were going to become triple bonds anyway. Okay, so that's it for that Lewis dot structure. So now we have this structure here. So we have 3. So basically we have the same number of atoms, same number of carbons and hydrogens here. So that's going to end up being 12 plus 4, that's 16 again. So this structure is going to look more like this. We have the 3 carbons bonded together. Again, those 4 hydrogens, symmetry is the way to go. So the best way is to put 2 hydrogens on this carbon here, 2 hydrogens on this carbon there. So I used 1, 2, 3, 4, 5, 6 bonds. That's 12 electrons. Subtract 12 from 16. I got 4 electrons. So I'm going to put them here on the central atom, or you could put them here on this carbon, on these carbons, right? So that would give these. So this is our central atom. We would put the lone pairs on the outer atoms first. Again, we want octet. So this one, we get an octet if we put 1 lone pair on this carbon, and we get an octet if we put 1 on this carbon. We could have put them both on here, but that wouldn't really be following the steps, because remember the steps, you put the lone pairs on the outer atoms first before your central atom. And so of the 3 carbons, this is the most central, so you would put them on there. But again, as you'll see, it doesn't really matter, because this carbon needs 2 more bonds, and so we need to move lone pairs, and we have 2 lone pairs, so we're going to have to move both of those anyway to form double bonds. So this lone pair is going to have to move to form a double bond there. This is going to have to form a double bond there. And so now we have our double bonds. Everyone's happy with an octet, so we're done there. Okay, finally, we've got our oxalate ion here. So count up the electrons. So remember, when you're counting up the electrons, don't forget the charge. So 2 carbons, that's 4 per carbon. That's 8 electrons, 8 valence electrons. And then we have 4 oxygens. So that's 6 electrons per oxygen. We're talking about valence electrons again. So that's going to be 24. So 24 electrons plus 8 is going to give us 32. And then don't forget the charge. We have a -2. That means we have 2 extra electrons. So we're going to add that to our total. So we have a total of 34 electrons. So we're going to draw our skeletal structure. So here we're going to have the 2 carbons bonded together. And again, symmetry, we have 4 oxygens. We're going to have 2 oxygens on each of the carbons. So 1 oxygen there, 1 oxygen there, 1 oxygen there, 1 oxygen there. And so now we used 1, 2, 3, 4, 5. 5 bonds, that's 10 electrons. So 34 minus 10 is 24. So now we're going to put electrons on the outer atoms, give them an octet. So we're going to put lone pairs. So here we're going to put 1, 2, 3, 1, 2, 3. Oops, let me write that better. Okay, 1, 2, 3, 1, 2, 3. So now that is 6 times 4 is 24. So we used up all of our electrons. So if you notice, this carbon and this carbon are both missing 1 more bond. They need 2 more electrons. So there's no lone pairs on the carbon, so we can't create a double bond from a lone pair on the carbon. So we're going to have to give a bond based on the oxygen. So we're going to have to take a lone pair from one of the oxygens on this side, create a double bond. So now this carbon has 4 bonds. And then we'll have to do the same thing. We'll take a lone pair from one of the oxygens on this side, create a double bond. And then there you go. So now we have our Lewis dot structure for this. Now I could have created a double bond here instead of there. I could have created the double bond here instead of there. So it doesn't matter. So now that everyone's happy with an octet, I got my Lewis dot structures. So now I can start to draw and label the structures. So the thing to keep in mind is whenever you have a double or triple bond, you always have one sigma bond and no more than one sigma bond. The rest of the bonds are going to be pi bonds. So if you have a double bond, you got 1 sigma and 1 pi. If you've got a triple bond, then you've got 1 sigma and 2 pi bonds. And the 2 pi bonds, or the pi bonds in general, are due to the overlap of unhybridized p orbitals, which is what I'm going to be showing in the drawing. So let's go ahead and get started. So here's my Lewis dot structure for this molecule. So they say we can use sticks for the sigma bond. So the hybridized sigma orbitals, we can use sticks. Hybridized sigma orbitals. So those are going to be the orbitals that are overlapping in between the along the axis of the 2 atoms. So so if you have 2 atoms, the straight line right in between them, that's the axis. So the orbitals that are overlapping along that axis right between the atoms, that's what we call the sigma bond. And so that's going to be represented by a stick. So if we draw this, right, so we have our hydrogen, there's a stick, right? And so this is going to be the overlap if I draw the oxygen, right? And then we have a stick, and then we have the nitrogen, and then we're going to have a stick. So here I want to, it's going to be hard to draw. So then we're going to have a line, and then we have our oxygen, and then we have the 2 lone pairs like so. We have our lone pair here, and then we have our 2 lone pairs here. Okay, so here are the sigma bonds. These are the bonds due to the overlap right between the atoms, like right along the axis. So here, the hydrogen has an unhybridized s orbital. And then here we have 1, 2, 3, 4 electron groups. That means that the oxygen, the bonding here involves the overlap of an sp3 hybridized orbital. So remember, the number of electron groups around your atom determines what hybridization there is. So for every electron group, you need to take an atomic orbital and hybridize those together. So since we have 1, 2, 3, 4 electron groups, that means we need 4 atomic orbitals. So if I kind of draw it here like so. So this would be my D, this would be my P, and this would be my S. So for every electron group around my atom, I need to take that many atomic orbitals and hybridize them to get the same number of hybrid orbitals. So in this case, since I have 4 electron groups, 2 bonding, 2 non-bonding, then I have to take 1, 2, 3, 4. I have to take an S, a P, a P, a P. I'm going to take those 4, and I'm going to hybridize them so I get 4 equal energy sp3 hybridized. So S and 3 P's gives me sp3 hybridized orbitals. So this here, if I label it, is going to be, how should I say, hydrogen with 1 S bonded or overlapping with the oxygen, which is going to be sp3 hybridized. So that's the labeling of that bond there. Okay. So then it would be the same here. So if I was to draw this, so here's my hydrogen with the 1s orbital, and then I have my oxygen here. It's going to have, an sp3. So this would be my 1s orbital, and this would be my sp3 hybridized orbital, and they're overlapping, forming the bond, right? And then I would have another sp3 hybridized orbital housing the two, each of the lone pairs, and then I'd have an overlap here as well. But they want us to represent that overlap as a stick, okay? So, not sure I'm going to have enough room here. I'll show it in a moment. Okay, so here we go. So then we got that overlap here. Again, here, this one, and I'm going to try to label it over here. So again, I have the sp3 hybridized. So one of the sp3 hybridized orbitals of the oxygen, right? So I have the oxygen with sp3 hybridized orbital bonding with the nitrogen. And you'll notice that here I have 1, 2, 3 bonding groups. Now, if you look over here, I have a double bond there. But when it comes to double and triple bonds, we only treat them as if they're one group, right? Even though there's two bonds there, we treat it as one group. So single bond is one group, a double bond is one group, a triple bond is just one group. So we have 1, 2, 3 electron groups. And so that's going to require 3 atomic orbitals. So in this case, it would be an S, a P, and a P. So that would be sp2 hybridized. So that's going to overlap with the nitrogen, which is sp2 hybridized. So that's what's going on there. There's an overlap of these two orbitals along the axis. And so this has an sp2, this is an sp2 hybridized orbital, and then you have overlap here. And now I'm going to label this one. So here again, you have 1, 2, 3 electron groups, right? So again, the oxygen here is sp2 hybridized. So if I'm going to label this one, then that's going to be, again, nitrogen, sp2, overlapping with the oxygen, sp2 hybridized. Okay, now, these are all sigma bonds that I have labeled, right? So no pi bonds yet, but here we have a pi bond, so that's going to involve unhybridized p orbitals. And so I'm going to use a different color to try to bring this out. Now, I'm assuming that these electrons here and this are all in the same plane. These electrons, this is trigonal planar because it's sp2 hybridized. This is trigonal planar because it's sp2 hybridized. And so all of this is going to be in the same plane. So this oxygen, this lone pair, these two lone pairs are all in the same plane. So I'm going to say that the plane of the board is what they're in. So when you have unhybridized p orbitals, they are going to be perpendicular to the plane, or they're going to be perpendicular to the axis. And so if I'm going to pretend that this is all in the same plane, then the unhybridized p orbital should be coming out of the board like so. So I'm going to try the best as I can. So here I have my orbital, p orbital going out of the board. Here it's coming, going into the board. Here it's coming out of the board. Let me get this out of the way so I can draw a better picture. And then here, the oxygen, it's going to have an unhybridized p orbital coming out of the board, and then it's going to go into the board like so. And so this is kind of perpendicular to the plane. And here's the plane of the board. Here's the plane of the molecule here. So again, we're assuming all this is in the plane. And these unhybridized p orbitals are coming out perpendicular to the board. And what you'll have here is overlap of the p orbital electron density here. And so again, this part here, this bond here is the sigma bond. So that's a sigma bond. This is a sigma bond. This is a sigma bond, right? But this overlapping where the unhybridized p orbitals are, that's your pi bond. So again, the way we label this is going to be the N, and that's going to be a p, like unhybridized p orbital, overlapping with a O unhybridized p orbital, and that's going to be a pi bond, right? So you can see that this matches. So we have one pi bond here because we have unhybridized p orbital on the N and an unhybridized p orbital on the O. How do we know that? Because both of these are sp2 hybridized. So sp2 hybridized N, sp2 hybridized N. So we used two p orbitals to hybridize. That left us one p orbital left over that was unhybridized. So since the oxygen and the nitrogen next to each other have an unhybridized p orbital, that allows it to overlap and form that pi bond if there's electrons in them, and there are. Okay, so that's how you would draw that one and label it. Let's go on to the next one. So the next one is going to be this one here. So let's go ahead and do that one. Okay, so let's do this one. So again, we're going to represent the sigma bonds by just the lines or the sticks. So since there's only single bonds here, they're automatically sigma bonds. The only time you have pi bonds is double and triple bonds. So you're always going to have a sigma bond between two atoms, always, right? And it's only ever going to be one sigma bond. You never have two sigma bonds between the same atoms. So we're going to represent this. So we'll draw it right here. So we have the carbon, right? This is going to be, I'll try to draw this as best as I can. So this is going to be a, tetrahedral, right? So then this is going to be like so. So there's kind of a tetrahedral, and this is kind of coming out of the board like so. Sorry about my drawings. So there's my next carbon, and so this is going to have a sigma bond, and there's my carbon, and then I have my other hydrogen, so that's going to be a sigma bond. So all of these are sigma bonds. And so if I was to label these, all three of these are the same, right? So if you look at the carbon here, it's got 1, 2, 3, 4 electron groups. So taking 4 atomic orbitals, 1, 2, 3, 4, so it's sp3 hybridized. So each of these is going to be an overlap of an sp3 hybridized orbital of the carbon overlapping with that of an unhybridized s orbital of the hydrogen, the 1s orbital, right? So here, and I'm going to kind of label all three of these. Right, so this is going to be the hydrogen 1s orbital unhybridized bonded to the carbon, which is going to be sp3 hybridized. So that's all three of those. And again, this is sigma. because this overlap is occurring between the two atoms along the axis. Now, what about these carbons here? Now, you'll notice here that there's a double bond, there's a triple bond here and a single bond here. So if we look at this carbon here, we have one electron group. Again, triple bonds are considered one electron group. We have one electron group here and we have one there. So there's two electron groups. So to form that hybrid orbitals, we need to take one s and one p. And so we get sp hybridized. So this carbon is sp hybridized. This carbon is sp3 hybridized. So then this bond here is going to be the overlap of the carbon with an sp3 hybridized orbital and a carbon with sp hybridized orbital. And again, this is going to be a sigma bond. And then if we go to this carbon here, which is this one here, you'll notice this is also sp hybridized because it's got two electron groups. And so this bond here, that sigma bond there, is going to be it's going to be the overlap of the first carbon, which is sp hybridized, with the second carbon, which is sp hybridized. Okay, so that I should say second and third carbon. So this is the second, this is the third, and again, this is a sigma bond. And lastly, we have the sigma bond here. And so this is going to be, again, this carbon here, which is sp hybridized. We're going to have an overlap with that carbon, sp hybridized, and then the hydrogen, which is just the 1s orbital, the unhybridized orbital. So that's what's overlapping here to form that sigma bond. So again, that is a sigma bond. Okay, so we've labeled all of our sigma bonds. Now, what about this triple bond? So again, what I said before about double and triple bonds is that they form because of the overlap of unhybridized orbital on adjacent atoms. Those are the atoms that are next to each other. So if we go back here to the hybridization of our carbons here, we said that they were sp, both sp hybridized. So that means we took an s and one p orbital, hybridized them, got two equal energy sp hybridized orbitals, but that leaves two unhybridized orbitals on both carbons. So both carbons have two unhybridized orbitals, and again, or p orbitals, I should say. And again, there can be overlap. So I'm going to try my best to draw a picture. I'm going to try to use clear colors. So again, we'll use green, and the green will represent the unhybridized p orbital going into and out of the board. Remember, these p orbitals are perpendicular to each other. Why? Because the s and the p and the y p orbitals are perpendicular to each other. So if they're unhybridized, they're going to be perpendicular to each other like normal. So again, I'm going to do my best to draw the lobes. So the lobe here is going into the board, and then the other lobe coming out of the board. Again, on this carbon, you're going to have a lobe going into the board. And let me get this out of the way. And then here you're going to have a lobe coming out of the board. And then let me use another color. Here, let me use orange. So this is perpendicular to the board, right? So if you can imagine or visualize that. So these green lobes are coming in and out of the board, perpendicular to the board. And then the other set of unhybridized p orbitals are going to be perpendicular to this. So if this is perpendicular to the board, then the other set is going to be in the board perpendicular. So if I draw it like this, so this is going up, and this is coming down, and this is going up, and this is coming down. like so. So if you can see that, I know it's hard to see, but they should be like crisscross to each other like this. So they're perpendicular to each other, right? So this green is in the line of the board, right? So they're perpendicular to the board here, and this is kind of up and down like in the board here. So then what you have here is you'll have an overlap of this on the top and bottom, right? So this is above, this is below, and then you'll have an overlap on this side. So this will be like right and left. So if I'm facing this way, then going into the board, that'll be on the left side. So if you can imagine, that overlaps there behind the board. And then this overlap here is in front of the board, right? So now you have one pi bond here. So this is a pi bond. The green is one pi bond, and the orange is another pi bond. And so that forms your triple bond. So you got the sigma bond in the middle. You've got the one pi bond top and bottom. You've got another pi bond left and right. So that's I think the best I can do as far as drawing. And then both of these, right, the orange and the green, these are both going to be your carbon with an overlap of an unhybridized p orbital with an overlap of another unhybridized p orbital. And so this is your pi bond, and there's two of them there. So that's the labeling of this. I hope this is helpful. Let's go on to the next one. We got two more. So I'm going to have to erase this and come back. So give me 1 second. I'll get out of your way so you can write this down in case you need to. Okay, welcome back. Now we have C. So let's go ahead and do this one here. Again, we're going to just draw the stick figure. So we have carbon, bond. Oops, here, let me write this a little bit higher to give myself some room. So we have C, and then bond, C, bond, C. And then we have two hydrogens here and here, here, and here. Okay, so we have all of our sigma bonds. So let's go ahead and label these. So all of these hydrogens are the same bonding. So you're going to have here, notice that this carbon here has 1, 2, 3 electron groups. So that's going to be sp2 hybridization, right? Because we're going to take an S, a P, and a P, one for each bonding group. And so that's going to be sp2 hybridized. And the same thing for this carbon here, 1, 2, 3 hybridized. So both carbons are sp hybridized, and there's going to be overlap with an unhybridized 1s orbital for the hydrogen. So all 4 of these are going to be the same. So let me go ahead and label those. All right. So all of those are going to be carbon. Oops, should do the hydrogen first. So it's going to be hydrogen with a 1s orbital overlapping with sp2 hybridized orbital. So carbon with sp2 hybridized, and again, those are sigma bonds. Okay. And so then the only thing left are we have two pi bonds. We have a pi bond between these two carbons. We have a pi bond between these two carbons. And so here, since this is sp2 hybridized, you're going to have one unhybridized orbital left for this carbon and also for this carbon. But notice that this carbon here has 2 electron groups, so that's going to be sp2 hybridized. So that means that it's got 2 unhybridized p orbitals on this carbon. So those 2 p orbitals, one unhybridized p orbital is going to form an overlap with this carbon here, forming your pi bond. And then the other pi bond, the other unhybridized p orbital is going to overlap with the unhybridized p orbital for this carbon, forming another pi bond. So let me draw what that's going to look like. Again, I'll do my best. So let's say I'm going to make, here, let me erase this. I'm going to draw a three-dimensional figure. For this one, we're going to say that the hydrogen is coming out of the board, and then the other hydrogen is going into the board. So that's going to be perpendicular to the board. And then these two are in the plane of the board. You'll see why I did that in a moment. Okay, so why? Because the p orbitals are perpendicular to each other. And so, again, so I have an unhybridized p orbital here. I'm going to do the green. Again, that's going to go into the board, and this is going to come out of the board like so. And so in this case, since this is perpendicular, this is a trigonoplanar shape, all of this is in the plane of the board. So the pi bond, the unhybridized pi bond is going to be perpendicular to this. So then we're going to have that unhybridized p orbital like so coming out of the board. Let me get this out of the way. And then this is going to go into the board, right? So then this is perpendicular to the board. And then on this side, remember, we need a pi bond over here. There's two unhybridized p orbitals on this carbon, but one on this. Since this green unhybridized p orbital is perpendicular to the board, then our other unhybridized p orbital is going to be perpendicular to that. So this will be up and down. So again, like so. And then this is going to be up and down like so. And so this is perpendicular to the plane. So remember, this is a trigonoplanar part of the molecule, but it's coming in and out of the board. It's perpendicular to the board. And so the unhybridized p orbital is going to be, perpendicular to that plane, which is going to be in the board. And so then what you get is you get overlap on the top and on the bottom. And then here you got overlap left and right. So again, this is going to be overlap in the front of the board, and this is going to be overlap in the behind the board, so left and right. And so you can see here that you can see now why these two hydrogens are perpendicular to these two hydrogens, because of the way that the p orbitals are aligned, right? So because this p orbital, this unhybridized p orbital is perpendicular to this unhybridized p orbital, the overlap has to be perpendicular to this overlap. So these two and these two hydrogens cannot be in the same plane. Okay, so I wanted to show that. So again, here, let me redraw this. So again, this and this, these are going to be the sigma bonds, and this too. Let me do that. And so then again here, the orange and the green are your pi bonds. So we have carbon with a p orbital, unhybridized p orbital, bonding or overlapping with another unhybridized p orbital. And that's the green and the orange. And so you can see we have a sigma bond here, right? Oops, I forgot to draw an arrow here. So here, I forgot to label these two sigma bonds. So let's go ahead and label those. That's going to be between your carbon with a sp2 hybridized orbital overlapping with a carbon with an sp hybridized orbital. So that's going to be that one there. And then we have, again, a carbon with an sp hybridized orbital bond overlapping with a carbon with an I said S but wrote P, an sp2 hybridized orbital. And again, that's going to be that one there. Okay. So that is that molecule. I hope that makes sense. And then finally, we're going to do our oxalate ion. I'm going to have to erase this because I took up a whole bunch of space for that one, but I'll give you a little time, a little moment to write this down. If you haven't done so, pause the video. I'll be right back. Okay, I'm back. That was quick. Okay, so now I have this one here. So let's go ahead and draw this one. This one's probably going to be a bit more difficult. So we have our carbon. We've got the oxygens here. I'm making them long so that way kind of give me more space to work with, I guess. Okay, so then I have my lone pairs. So I'll have 2 on this one, I'll have 2 on this one, and then these I'll have 3, and these I'll have 3, like so. Okay, so the sigma bonds. So for this sigma bond, or I should say, let's do these. So for these 2 sigma bonds, they're going to be the same because this carbon here is going to be 1, 2, 3, got 3 electron groups, so that's sp2 hybridized, right? Because we need 1 s and 2 p for the 3. So, and then the oxygen is going to be 1, 2, 3, 4. So we got 4 electron groups, so we need 4 atomic orbitals. 1, 2, 3, 4. So it's sp3 hybridized. So this is going to be the overlap of carbon with sp2 hybridized orbital with an oxygen sp3 hybridized orbital. So those are going to be those 2 there. This is again sigma. Okay. And then these 2 are going to be the same as well, right? So we're going to have those 2. So again, this is going to be sp2 hybridized. This is going to be sp2 hybridized. So this is going to be 1, 2, 3. So that's going to be sp2 hybridized as well. So those 2 we're going to have, for these 2, we're going to have oxygen with sp, well, let's do carbon first. I guess it really doesn't matter, but I just like to do carbon first. So carbon is going to be sp2 hybridized, bonding or overlapping with oxygen with a sp2 hybridized. So those are the 2 orbitals that are overlapping to form the sigma bond here. So again, that's going to be sigma. Okay. And also this bond here, we should do that one. So that bond there is between the 2 carbons. So we just said that this is going to be sp2 hybridized. This is sp2 hybridized. So then there we have the carbon, the first carbon is sp2 hybridized, overlapping with the sp2 hybridized orbital on that carbon. So that, again, this is a sigma bond. So we have 5 sigma bonds. Okay. All right, so now that we got the sigma bonds, we got to look at the pi bonds here. So we have a double bond, double bond. So each of those has 1 pi bond. So that means that we've got an unhybridized p orbital, which makes sense because we got sp2, sp2. So this is sp2 hybridized, this is sp2 hybridized. So we got an unhybridized p orbital on the carbon, and we got an unhybridized p orbital on the oxygen. Those are going to overlap, right? So if I draw as best as I can, I don't know how well this is going to go, but I have 1 here. So if I get those out of the way, if I can kind of bring these this way, And so I'm going to have, let me get rid of that for a moment. So I'm going to have, let's say, unhybridized p orbital there. And on this carbon, I'm going to have an unhybridized p orbital there. So I'm going to get overlap here. Okay. And then for this one, same thing. So if I can get rid of those, put them on this side a little bit. So then here, again, maybe that's like that, and that's like that. And then I'm going to have an orbital here. So these are unhybridized. So then that's going to form overlap like that. And so those are going to be my unhybridized p orbitals overlapping. And so again, for this one here and for this one here, if I can draw this, these are going to be my carbon sp, oops, not sp, sorry. It's going to be my unhybridized p orbital overlapping with the oxygen with an unhybridized p orbital. And so those are going to be my pi bonds. So both of those are my pi bonds, like so. And so that is how you would label your molecules. So again, you start with the Lewis dot structures. Lewis dot structures will show you where the sigma and pi bonds are. And then when you want to label them and draw them, this is the way to do it. I hope this was helpful. If this helped you in any way, if my drawings were good enough, please let me know down below. If this helped you in any way, then please do me a favor, like the video, share the video, hit that like button somewhere over here, find it, it's there, click on it. Also, do me a favor, support the channel, subscribe, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you would like me to go over, or if you have a question, or if you have a topic you would like me to cover, I would be happy to do that for you. Put that down below. Thanks for joining me and have a great day.